have you ever tried to imagine, like, pinning down the location of something super tiny, like an electron? We're talking smaller than a billionth of a meter here.
Yeah.
And here's where things get really wild.
Okay.
Electrons, they can act like particles, like tiny marbles, right? But also like waves, kind of spreading out like ripples in a pond.
Right.
How can something be in two places at once? It's crazy.
That's really the mind-boggling nature of quantum mechanics, you know?
Yeah.
It just throws our everyday intuition right out the window.
Yeah.
The idea that an electron can be both a particle and a wave is one of those central mysteries.
Okay.
And it leads us directly to this thing called the Heisenberg Uncertainty Principle.
Okay, so the Heisenberg Uncertainty Principle.
Right.
It's not just about our instruments being like fuzzy, right?
Yeah.
It's something deeper.
Exactly, yeah. It's a fundamental law of the universe. It's baked into the fabric of reality at the quantum level. The more precisely we try to lock down an electron's position, the less we can know about its momentum, like how fast it's moving and in what direction, and vice versa.
Okay, so there's this inherent trade-off between knowing where a particle is, knowing how it's moving.
Exactly.
Wow.
To understand this, we really need to start thinking in terms of wave functions.
Okay.
It's not that the electron is just randomly zipping around, you know, it's not just chaotic.
Yeah.
Instead, its behavior is described by this thing called a wave function, which gives us the probabilities of finding it in a particular state.
Hold on. Wave functions.
Yeah.
I'm picturing, waves crashing on a beach, but that can't be right for something as tiny as an electron, right?
Good point, yeah.
Yeah.
Think of it more like a bunch of waves.
Okay.
Each with a different wavelength, all layered on top of each other.
Uh-huh.
This creates something called a wave packet.
Wave packet.
Yeah. Which helps us visualize where the electron is most likely to be found.
Okay.
A tight, narrow wave packet means we have a pretty good idea of the electron's position.
So a skinny wave packet, we know roughly where it is.
Right.
But didn't you say there's a trade-off?
You got it.
Okay.
The trade-off is that the momentum, how the electron is moving, becomes super uncertain.
Really?
It's like trying to photograph a speeding race car.
Okay.
A short exposure freezes the car in place, but you can't tell how fast it was going.
Ah, I see.
Right.
So a blurry race car photo is like a wide wave packet.
Exactly.
We know it was moving fast, but we don't know exactly where it was at any given moment.
Right.
So we can either have a sharp position, but a blurry momentum, or vice versa.
Right.
No way to get both sharp at the same time.
You nailed it.
Wow.
And the math behind this is fascinating.
Okay.
It shows this link between position and momentum. It's as if they're on a seesaw. You push down on one side and the other shoots up.
Yeah.
You can't have both sides down at once.
Wait, so it's not just some vague idea.
Yeah.
There's actual math that shows you can't know both things at the same time.
Absolutely.
That's incredible.
The relationship between position and momentum is described mathematically by something called the Fourier transform.
Fourier transform.
Yeah.
I've heard of that.
And here's the kicker.
Okay.
This mathematical relationship isn't just some theoretical abstraction.
Right.
It has real-world consequences that we see all around us.
All right, you've got me hooked. What kind of crazy things happen because of this uncertainty principle? Give me an example.
One of the most mind-bending examples is quantum tunneling.
Quantum tunneling.
Yeah.
Okay.
Because we can't know both the position and momentum of a particle with perfect accuracy. There's a chance it can tunnel through barriers that it shouldn't classically be able to cross.
Wait, are you telling me that particles can just slip through walls?
Not exactly slip through.
Okay.
Imagine throwing a tennis ball at a wall.
Okay.
In our everyday world, the ball either bounces back or, if it has enough energy, it breaks through.
Right.
But in the quantum world, the ball, or in this case, a particle, has a tiny chance of appearing on the other side of the wall.
What?
Almost as if the wall were a ghost.
Okay, that's seriously weird.
Right.
But how does this quantum ghosting actually happen?
Yeah.
Does the particle just vanish and reappear?
Not quite.
Okay.
It's more like the particle has a tiny probability of existing on the other side of the barrier.
Okay.
And the uncertainty principle makes it possible for that probability to become a reality.
Really?
It's as if the particle borrows some energy from the uncertainty and its momentum
Wow.
to overcome the barrier.
So the fuzziness, the uncertainty, actually gives the particle a chance to do something it shouldn't be able to do.
Exactly. And this isn't just some theoretical curiosity.
Yeah.
It's what makes technology like semiconductors.
Okay.
And therefore, all our computers and smartphones possible.
You're telling me my phone works because of quantum ghosting?
In a way, yes.
Wow.
And it doesn't stop there.
Oh, no.
The uncertainty principle has implications
Okay.
for all sorts of amazing things.
What else? What else?
From quantum computing to the way we measure light from distant stars.
Okay, I need to take a breath here.
Right.
This is a lot to process.
Yeah.
So we've got tiny particles acting like both waves and particles.
Uh-huh.
We've got this inherent uncertainty
Right.
in their position and momentum.
Yeah.
And we've got quantum tunneling, where particles can essentially ghost through walls.
Right.
And you're saying this is just the tip of the iceberg.
Just the beginning.
Oh, boy.
And the deeper we dive,
Yeah.
the more we see how this principle,
Oh.
discovered by Heisenberg,
Yeah.
has profound implications
Okay.
for our understanding of the universe.
Wow, this
Yeah.
is big.
It is.
Okay, I'm ready for more.
All right. Welcome back to our deep dive. You know, it's not just about the weird behavior of particles.
Oh, okay.
It also has some pretty profound philosophical implications.
Okay, philosophical.
Yeah.
So we're moving beyond the physics now.
You could say that for centuries, physicists believed in a deterministic universe. You know, if we knew the initial conditions with enough precision,
Yeah,
we could predict everything.
right.
But the uncertainty principle kind of throws a wrench into that neat picture.
Hold on. Are you saying that because of this principle,
Yeah.
the future is fundamentally unpredictable?
It certainly suggests that
Oh,
at the quantum level, things aren't set in stone.
really?
Instead, we have probabilities and possibilities,
Okay.
a kind of fuzziness built into the fabric of reality.
Huh.
Think about it at the tiniest level.
Yeah.
The universe isn't this perfectly predictable machine after all.
So our classical view of a cause and effect universe
Yeah.
starts to break down when we look at the quantum world.
Exactly, yeah.
Wow.
The uncertainty principle challenges our very notion of cause and effect.
Okay.
And it goes even deeper.
Deeper.
For ages, philosophers have been debating about free will.
Oh, right.
Do we truly have choices?
Yeah.
Or is everything predetermined?
Right.
This principle throws a whole new layer of complexity into that debate.
Wow. Okay, so if we can't predict the future with certainty,
Yeah.
does that mean free will is back on the table?
It is indeed.
I mean, that's a huge philosophical question, right?
It is. It is.
Yeah.
If the universe is inherently probabilistic
Yeah.
at the quantum level,
Uh-huh.
does that mean there's room for genuine choice?
Right.
Or is it all just a cosmic dice roll? We still don't have definitive answers.
All right. I can already feel a headache coming on from thinking about all that.
Right.
Maybe we should step back from the edge of the philosophical bliss for a second
Okay.
and bring it back to something a bit more concrete.
Fair enough. Let's
Yeah.
let's look at some practical implications.
Okay.
We've talked about quantum tunneling
Right.
and how it affects technology,
Yeah.
but the uncertainty principle also impacts other areas of science and engineering. Like what? Give me another example.
Yeah.
Where this uncertainty principle has real-world consequences.
One fascinating area is the development of ultra-precise clocks.
Ultra-precise clocks.
You see, the more accurately we try to measure time,
Yeah.
the more uncertain the energy
Okay.
of the system being measured becomes,
Yeah.
and vice versa.
So even time itself
Yeah.
is subject to this uncertainty.
Exactly.
That's wild.
It puts a fundamental limit
Okay.
on how accurately we can measure time.
Really?
It's like trying to pin down
Okay.
both the exact moment a wave crashes on the shore
Uh-huh.
and the exact energy it carries
Okay.
at the same time.
Got it.
The more you try to nail down one,
Yeah.
the fuzzier the other gets.
So there's a limit to how precise our clocks can be.
No matter how advanced our technology gets,
It seems that way.
that's both frustrating
Yeah.
and fascinating at the same time.
It is. It is. And it has implications for everything from GPS navigation,
Okay.
which relies on incredibly precise timekeeping,
Right.
to scientific experiments that require measuring time
Uh-huh.
with incredible accuracy.
Okay, that makes sense. But wait,
Yeah.
there's something else that's been bugging me.
Okay.
I remember reading somewhere that the uncertainty principle actually prevents atoms from collapsing.
Absolutely.
Is there any truth to that?
This is one of the most amazing consequences
Okay.
of the uncertainty principle.
Yeah.
According to classical physics, electrons orbiting an atom should constantly be emitting radiation, losing energy and spiraling inwards until they crash into the nucleus.
Right, so they should just...
They should implode, but we know that's not what happens.
Right, atoms don't just spontaneously implode.
Exactly.
So what's stopping them from collapsing?
You got it, the uncertainty principle.
No way, really.
If an electron were to get too close to the nucleus, its position would be known with great accuracy.
Right.
And remember, if we know the position with high certainty, its momentum becomes extremely uncertain.
Right.
This uncertainty in momentum gives the electron a kind of kick, preventing it from spiraling into the nucleus.
So the uncertainty principle is like a cosmic safety net.
You could say that.
Preventing the universe from imploding? Yeah. That's a pretty important job.
It is indeed.
Wow.
It's one of the fundamental principles that governs the stability of matter as we know it.
Right.
And without stable atoms, we wouldn't have stars. Yeah. Planet. Or, well, us.
Okay, I'm starting to see the bigger picture here.
Good.
The uncertainty principle isn't just some abstract idea.
Right.
It's woven into the very fabric of reality.
Absolutely.
Affecting everything from the behavior of atoms to the precision of our clocks. Then the possibility of free will.
That's exactly right.
Wow.
And it forces us to rethink our fundamental assumptions about how the universe works.
Yeah.
Instead of a clockwork universe where everything is predictable, we have a universe where chance and probability play a fundamental role.
Right.
It's both humbling and exhilarating.
It is. So we've seen how this uncertainty works.
Yeah.
And we've dipped our toes into the profound implications it has on everything from the stability of atoms to philosophical questions about free will.
Right.
What else can we uncover about this amazing principle?
I'm glad you asked.
Welcome back for the final part of our deep dive into the Heisenberg Uncertainty Principle.
Yeah.
We've covered a lot of grounds.
We have.
From wave packets to quantum tunneling to the philosophical implications of an uncertain universe.
Yeah.
But I have a feeling there's even more to uncover.
There's always more to explore.
Yeah.
Especially when we venture further into the quantum realm. One area that's particularly intriguing is the phenomenon of quantum entanglement.
Okay, entanglement.
Yeah.
That sounds familiar. Is that the one where two particles are somehow linked together?
Yes.
Even if they're miles apart?
Exactly. It's like they have this invisible connection.
Wow.
A bond that transcends space and time.
Okay.
Measuring the state of one particle instantly influences the state of the other.
Really?
Regardless of the distance between them.
Hold on. Are you saying they can communicate faster than the speed of light?
Wow.
That seems impossible.
It's not communication in the way we usually think about it.
Okay.
It's more like they share a deep fundamental connection, as if they were two sides of the same coin.
Right.
And you guessed it, the uncertainty principle plays a key role in understanding this bizarre phenomenon.
Right. I'm on the edge of my seat. How does uncertainty fit into this entanglement puzzle?
Well, remember how we can't know both the position and momentum of a particle with perfect accuracy?
Right, right.
When two particles become entangled, their uncertainties become correlated. It's as if their wave functions merge, even if they're physically separated.
So if you measure one entangled particle, you instantly know something about the other.
Yes.
Even if they're light years apart.
That's the strange thing about entanglement.
It's like they're magically connected.
It's not magic, but it does challenge our classical understanding of locality and separability.
Okay.
Measuring one particle collapses the wave function of both particles simultaneously.
Wow.
Regardless of the distance between them.
This is getting seriously mind-bending, but it's also incredibly exciting.
It is.
What are the implications of this entanglement? Does it have any practical application?
Absolutely. Quantum entanglement is at the heart of many emerging technologies.
Like what?
Including quantum cryptography, which uses entanglement to create unbreakable codes.
Wow.
And even more powerful, quantum computers. That can solve problems beyond the reach of classical computers.
Didn't we talk about those earlier?
We did.
How does entanglement make them even more powerful?
Think of it this way. By entangling multiple qubits. the building blocks of quantum computers, we can create a network of interconnected particles that can explore many possible solutions simultaneously.
So they're working together.
They are.
Okay.
This massive parallelism allows quantum computers to tackle problems that would take classical computers billions of years to solve.
That's incredible.
It is.
And to think it all stems from this inherent uncertainty at the quantum level. It's like a key.
It is. It is.
That unlocks the hidden potential of the quantum world.
It certainly is, and the exploration of this potential is still in its early stages. Scientists are constantly pushing the boundaries, conducting experiments that test the limits of the uncertainty principle, and explore its implications for our understanding of the cosmos.
So there's still so much we don't know.
Absolutely.
Right.
We're just scratching the surface of what's possible.
It's mind-blowing to think about what new discoveries lie ahead. But before we wrap up, I want to touch on something we've hinted at throughout our conversation, the philosophical implications of all this. Does the uncertainty principle fundamentally change how we view our place in the universe?
I believe it does.
Yeah.
It challenges the deterministic worldview that dominated scientific thought for centuries.
Okay.
Instead of a clockwork universe where everything is predetermined, we have a universe where chance and probability play a fundamental role.
So instead of being cogs in a machine, we're participants in a universe full of possibilities.
Exactly.
Wow.
This shift in perspective has profound implications for how we think about free will. Consciousness, and even the nature of time itself.
It opens up new avenues for philosophical inquiry, urging us to reconsider what it means to be human in a universe governed by quantum laws.
Absolutely.
It's both humbling and empowering, isn't it?
It is.
We're part of something much grander and more mysterious than we ever imagined.
Absolutely. And I believe that embracing this uncertainty, this sense of wonder and possibility is key to unlocking the true potential of the human mind and spirit.
I couldn't agree more so as we conclude our deep dive into the Heisenberg Uncertainty Principle. I encourage you to keep questioning, keep exploring, and keep embracing the mysteries of the universe. The more we delve into the quantum realm, the more we realize how much we still don't know.
Yes.
And that's what makes this journey so exciting. Thanks for joining us.